In this video, we're going to have a look at the identity matrix. In fact, if you've watched the video about basic concepts in abstract algebra, then you'll know that we should really be more specific and define both a set and an operation when talking about an identity element. For instance, if we define the pair shown here, where I've used this notation to refer to the set of P by Q matrices, then the identity element is the P by Q matrix which consists of all zeros. However, in the case of matrix algebra, the term identity matrix is almost always used to refer to the multiplicative identity for a set of square matrices. We'll consider the pair shown here, where M subscript n denotes the set of n by n matrices and the operation dot refers to matrix multiplication. I'll denote the identity element for this set by a capital I. The identity element must be an n by n matrix because it has to be a member of the set Mn. We can add a subscript n here to make the dimensions of I explicit, but in general we don't need it because this property can be inferred from the set under consideration. The identity matrix, that is, the multiplicative identity matrix, must satisfy this result here. Where X is any n by n matrix. Let's think back to how matrix multiplication works and look at the first part of this expression. Element-wise notation can be helpful here. The ijth element on the left must be the same as the ijth element on the right in order for the expression to be true. And the ijth element on the left is given by the sum over all elements in the ith row of X multiplied by the corresponding elements in the jth column of I. Notice that we can satisfy this expression by making the kjth element of matrix I equal to a 1 if k equals j, and a 0 otherwise. In that case, the summation on the left just simplifies to give a single element xij. The expression given here defines the elements of the identity matrix, but we do need to verify that this also satisfies the other part of the definition. That is, we need to verify that the ijth elements of Ix are the same as those in the matrix X. Writing the elements on the left as a sum again, we can see that the expression can be satisfied by making the ikth element of the identity matrix equal to a 1 if I equals to k, and a 0 otherwise. So that again, the summation on the left simplifies down to a single element. These two definitions here are equivalent. And so by constructing the identity matrix in this way, we can satisfy its definition. Let's examine what the n by n identity matrix looks like. We'll look at the 2 by 2 identity matrix, and the 3 by 3 identity matrix in particular. The definition states that elements with the same row and column number are a 1 and all of the other elements are zeros. You could define some other arbitrary 2 by 2 and 3 by 3 matrices. And try multiplying out the products I2 x2 and x2 I2, or I3 x3 and x3 I3, and verifying that both of these expressions are just the same as x2 and that both of these expressions are just the same as x3. This will give you a feeling for how the identity matrix works. Looking, for example, at the multiplication I3 x3, we can see that when we multiply a row by a column, the row effectively selects one item from the given column in X. In general, the n by n identity matrix has all ones on the leading diagonal and all zeros everywhere else. Let's have a quick look at one of the ways in which the identity matrix can come in useful. Let's suppose we have an equation given by AB plus lambda B is equal to C, where A, B and C are square matrices and lambda is a scalar, which could be complex, but let's just suppose it's real here. It is tempting to try to group together the expressions on the left to obtain the result A plus lambda times by B is equal to C. But remember, these are matrices we're dealing with here. This represents matrix multiplication, and the quantity A plus lambda would require us to add a scalar to a square matrix. And this is not a valid matrix operation. Instead, we note that B is exactly the same as I times B, where I is the identity matrix that's the same dimensions with B. And so we can write this expression here as AB plus lambda IB is equal to C. And then we can group the expression like this. The grouping is perfectly valid since this quantity here involves adding a square matrix to a square matrix with the same dimensions. So this forms a new matrix which we could call X. And this gives us a problem of the form XB equals to C, where all three of these matrices are the same order. Shortly, we'll learn how to solve problems of this type.